Hi, welcome to my YouTube channel. In our today's video, we are going to go through 6 rules used in block reduction, and at times you may be told to reduce a certain block diagram to canonical form, and then you can be told to get the ratios. For example, you can be told to get the transfer function, that is the CR ratio. Now, what I mean by a canonical block diagram is a diagram with one feedback element and one input. Consider the rules that follow. Now, our first rule is when we have gains that are arranged in series. Now, when combining the gains in series, it is just equivalent to getting the product of each gain. So it will be G1 times G2 times G3. So it will be equivalent to this diagram over here. By doing so, we will have reduced it. Now, the second rule is combining gains in parallel. Okay, note the difference between parallel and series is that for a parallel there is a summing point. So at this point where we have parallel gains, it is equivalent to getting the sum. Okay, the sum of the two gains. So here I've placed plus or minus because the state here can either be positive or minus. So when it is a positive, we are going to add G1 plus G2. When it is a negative, it will be G1 minus G2. Now we will get this block diagram here. So that is the reduced block diagram of this. Now the third part is removing a feedback loop. Now when removing a feedback loop, for us to achieve the reduction in such a diagram, we'll have to get the CR ratio, that is the transfer function, and transfer function is got by this formula: G all over 1 plus or minus our gain of G times our feedback. The difference between a feedback loop and gains in parallel is basically the direction of the arrows. For our gains in parallel, the arrows are always in a forward loop, but in a feedback loop, this arrow over here, which forms the feedback loop, it is said to be a feedback because the arrow is pointing towards the reverse direction. We are proceeding to our fourth rule, changing a summing point. You may be given 2 summing points, and you are told to reduce that particular block diagram. So this diagram is equivalent to this diagram. Only note that our value of x4 must remain unchanged. So here our x4 is x1 plus x2 minus x3. Okay, so it is in this diagram. Now our fifth rule is shifting a summing point. Shifting a summing point. This is what we call a summing point. So at times we may be expected to shift a summing point ahead of a gain. Now for us to achieve that, we are going to multiply our x1 times the gain times the gain which we are shifting ahead of it. Now after shifting ahead of this gain, we'll obtain this diagram. And take note, when shifting, the value of x3 here should remain unchanged. For example, here our x3 is x2 plus x1, then we multiply by g. That is our value of x3. So we expect the value of x3 to remain the same at this block diagram. So our x3 here after multiplying this x1 multiplying this x1 with the gain. So our x3 is equals to x2 times g plus x1 times g. By factoring out g, we will have x2 plus x1 into brackets g. So it has remained unchanged, and it should be like that. If we find by any means when shifting a summing point, our value of x3 is not the same, we will have created our own rule. Now our sixth rule is shifting a takeoff point. This is what we call a takeoff point. We may be expected to shift this takeoff point ahead of a gain, and for us to achieve that, to divide our x2 by this gain. This block diagram over here will be equivalent to this block diagram, and if you want to reverse it, okay, we are just going to multiply this value here by our gain. Please note the difference between shifting a summing point and shifting a takeoff point. Okay, when shifting a summing point, we multiplied our x1 by the gain to obtain this diagram. But when shifting a takeoff point ahead of a gain, what we do is that we divide by the gain. Okay, and we obtained this diagram, which is equivalent to this diagram over here. Right. Okay, thank you for watching. Don't forget to like, subscribe, and share the video.